All right. Hello all. Thank you for coming. Sorry for this last-minute change in the lecture room. So this is my PhD proposal defense, and the proposal title is Understanding a Block of Layers in Deep Neural Networks from an Optimization Perspective. So just to make sure that we're all on the same level of understanding, we can think about deep learning as just a rebirth of neural networks, right? And for the sake of this proposal, the best way to look at it is basically just a collection of some mathematical functions in a compositional way. And they are excellent methods for understanding data. But what do I exactly mean by understanding data? Well, there's lots of progress in the computer vision community that happened lately, in which we'd like to build up a model that can perform semantic segmentation, object detection, for applications like self-driving cars and so on. And of course, there have been lots of progress as well in different areas in terms of defeating world champions at different games like StarCraft and Dota 2, and professional human players at the game of Go, and also professional players at playing chess. Of course, we have done that a long time ago, but just very recently we defeated the most powerful chess engine that we know of. All right. So one way to look at the deep learning is just this one block of compositional functions, and you just query about some image, and would like to know what is the output of this network. And in this case, I mean, just classification example, this is my face, and this is what the network thinks I am doing for the past 2 years. Okay, but for practical perspectives, it's just sufficient to look at this as black box perspective, in which we don't really care about what happens really in the machinery behind this network, so long as it's regressing the function that we're looking for very well. So there has been progress people doing in terms of knowing what really happens, but this has collected momentum just recently when people have shown that it is rather easy to generate adversarial attacks. So what do I mean by this? It seems that rather simple to generate a small imperceptible noise. You add it to some input image, and all of a sudden the performance of the classifier just drops and thinks this panda is given, and with a high confidence too. And apparently one can do that with just perturbating just a single pixel in that. And there are lots of progress in that, which people also have shown that apparently you can generate these deterministic samples. You add to any image, to any network that you wish, and you still destroy the network's performance. So all of this has driven lots of research towards understanding what happens, but the problem is just too difficult from a holistic view. Just because networks come at all shapes and sizes. You have ResNet connections, dense connections, autoencoders, and even a variety mix of all of these things, which are usually task-specific. So it seems that tackling this from a holistic view is just somewhat difficult. And what we want to do through this approach is just to look at one fundamental block. So despite this high dissimilarity between networks, they still share more or less the same block, at least during training, which is represented through dropout layer, affine mapping, and then another nonlinearity. So what we really want to do is to go this bottom-up approach and understand everything that we can about this function from different perspectives, and maybe potentially extend these results to larger networks and make use of them from some perspective. So the presentation will go as 3 pieces, but think about them as the 2 pieces somehow do not seem necessarily directly related to deep learning, but they will lie the ground for some of the tools we'll use later on for our final conclusion at this deep layers stochastic solver section. So if we start with the first work, FFTLasso, which is basically fundamental, we would like to solve some optimization problem that is simple and very easily motivated, at least from a computer vision perspective, since it has been used for a long time by now. So it's nothing but, from face recognition perspective, that we want to perform classification, in which one can take just vectorized image patches of different people and collect them as blocks into some big dictionary matrix A. Once we solve this problem, we'd like to inquiry about what class does B belong to. And by looking at the solution set, you look at the density and the sparsity of that vector C, and that gives you an indication to what class does C might actually belong to. So what we really want to do is basically investigate this a little bit more, potentially investigate different solvers or reformulation of the same problem that benefits us from somewhat different perspective. And for the sake of this presentation, we'll fixate on first-order solvers in deterministic settings, maybe solvers that also can handle linear constraints for the sake of generality of the problem. It has been shown several times before that it is very, very powerful to use ADMM to solve such a problem in the dual domain. And the reason behind this is because usually the dictionary or matrix A is often very, very fat, in which it has very few number of rows. in which the ADMM just require at most per iteration complexity, inverting very, very small linear systems are of size m by m, where m is the number of rows. And such a nice solver can also handle linear constraints for more general settings. What we really want to do is maybe either adjust the solver or come up with a reformulation with the LASSO itself, such that we apply ADMM and gain something out of it, and potentially something that allows for high parallelism across maybe multiple GPUs. All right, so what do we do here? So the basic idea is extremely simple. So we start with a LASSO problem, and then we say, okay, let's take the first column in this big dictionary and do something that seems nonsensical at the beginning, which essentially we take each column and generate a block segment matrix out of it. And we do this for every single column in the dictionary A, and this will result us in having a much bigger problem than what we started with. And to make sure that both problems are equivalent, basically we just force those elements that have that interact with those synthetic columns that we have added, we force them to be exactly zero. So both problems are similar, but it seems like non-intuitive. Why would you introduce constraint on a problem that's even bigger than what we started with? So let's look at some of the insights of this new problem and how it looks. Well, we have linear constraints and the problem is big, but if we write this A tilde C tilde much more differently, we get that it's actually doing some form of convolutions, and these convolutions arise because of these circulant matrices that happens that interact with blocks in the solution vector C tilde. But what is surprising to us is that this actually looks very, very similar to an inference step in a problem very well known in vision, which we'll talk about later, which is convolutional sparse coding. But the only exceptional trick is that there is linear constraints. And if you look at these linear constraints more closely, it seems that you are constraining the sparse codes to belong to the set of impulse functions. So it's like you're doing inference step of convolutional sparse coding, but the sparse codes are not arbitrary, are just impulse functions. So basically you see how you recover back the original problem. Okay, great. So now what you see is that there's some form of equivalence between fully connected layers, which can be represented as an unstructured matrix A capital multiplied by some vector C, which in neural networks somehow, which this is for now hand-wavy, represent a fully connected operations. And it seems like it's doing something similar to convolution, but in higher dimensions, and both operators seem to be equivalent to some extent. Okay, so we'll keep this for now, and we'll discuss it later on in more detail, but let's keep this high-level idea at hand. So what we're going to do is something really simple. I'm going to apply ADMM again, but on the dual version of this lifted problem, and this is what we'll refer to FFTLasso. So still applying ADMM, but in the dual version of the lifted problem. So what is the benefit? I mean, why did we do all this hassle from the get-go? Well, it turns out that those linear systems that you get, which are highly structured of these circular matrices, can be solved with element-wise operations. So you're still solving linear systems, but the most expensive operations take Fourier transforms. And the complexity of these can be significantly reduced by taking n log n complexity with fast Fourier transforms. We do some extra step, which we do Nestoff's like update on the dual variables as well. Okay, so what happens? What's happening regarding the complexity? Well, worst case scenarios in the original problem, you'd have to invert linear systems, which is worst case scenario you have to do in cubic sort of operations, where m is the number of rows. But with FFTLasso, you see that you're doing Fourier transforms and you're doing element-wise operations, so it's around complexity mn log m. So there is a regime of matrices where this actually is suited, where you reduce the number of computation. But then how will we compare the two methods together? Well, as I mentioned, since this is element-wise operations, we can trivially parallelize it on GPUs. So what you see here is, on each plot, is experiments on different GPUs, where you see the comparison of two methods, where the horizontal x-axis at 0, so long we're below it, that means we're doing better. And it seems as the dictionaries grow larger and larger, we're doing better than doing just the dual ADMM in the dual version. And you see these kinks in performances, but these are related to fast Fourier transforms, and they are somehow optimal at powers of 2. So we do some more experiments by adding Nestoff's to original dual problem and see how much both problems benefit from it. It seems that FFTLasso also benefits from it more, just because of adding this structure and increasing the dimensionality affects the condition number somehow, in which we benefit more from this acceleration. Okay, so the problem before that, the dimensions of the problem couldn't exceed them beyond 8,000 by 8,000 square dictionaries. Well, that's because of a GPU limitation issue. So we got our hands on this Quadro P6000 GPUs, which can, I think, having 24 gigs of memory. We managed to push this all the way until 16,000 by 16,000 dictionaries, and we observed somewhat similar speed up and performance. Okay, so is that all? Well, the thing is that there are problems where you can't actually apply the original problem, which is situations where the dictionary A is just so massive that you can't fit into one GPU. You can't even put it on potentially a RAM. So what you can do is basically, as you see, since the operations are element-wise, well, just trivially break it vertically, throw each piece into GPU, and do all operations independently and aggregate the result vectors of length m, which is the number of rows, and send it back again. Well, one would say, well, if m is too large and you can't even communicate this, what could we possibly do? The bottleneck is that we still need to compute Fourier transforms of vector of length m. So is it possible to split that vertically, horizontally as well? It turns out, yes, you can. So now you can actually split this matrix however you wish, but you'd have to use one extra trick, and that trick basically relates to how would you compute Fourier transforms of long vectors with respect to Fourier transforms of individual pieces. So you still need to communicate vectors, but they are much smaller than what we started with. So of course we did some face recognition experiments, and it seems that if we compare that also with a different metric, which in this case is the classification accuracy for the face recognition task, we're still doing well, not only in minimizing the objective. All right, so it seems like it's easily distributed. There are also some experiments on memory efficiency of the method and so on, but also it can handle linear constraints as well, because the solver itself can handle linear constraints. So, and this is not necessarily restricted to one norm regularizers, but other regularizers are simple enough and can have element-wise proximal operators. So, but LASSO problem is very well appreciated, at least in the vision community. Okay, so the other piece, so up until now I didn't talk about deep layers or deep networks in general, but I'll talk about it once we finish this tensor CSC things. But why convolutional sparse coding, which is a problem I will clearly define in a moment, is because we've seen those LASSO problems somehow relate to convolutional sparse coding, and these fully connected operations, unstructured matrix multiplication with respect to structured matrix or convolutions are equivalent some high dimensions. So I'd like to spend some time investigating this a little bit further. So what is, so this is the overall, skip this slide for a moment, but basically, basically what we want to do is to look at this CSC and see how it relates back to convolutional neural networks, specifically that there is lots of progress showing CSC is tightly related to deep networks. So let's start by defining the problem. The problem is also extremely simple to motivate, and basically it starts with an assumption of how the images are formed in the human brain. And the way people say, well, okay, any given image X is represented by the sum of convolutions between some sets of sparse maps given in ZK, and some dictionary elements DK. So, well, how would we use this to learning generic dictionaries? Well, that is simple, right? You just put down reconstruction error. You say, I don't know these X's, I don't know these dictionaries, I'll just optimize for them over a large set of training samples in capital. And this is where you see one norm of the sparse codes, and these are your filters. So now what you hope to do is that once you solve this for a large number of dictionaries N, or training examples N, you hope that you have learned generic dictionaries that you can use to reconstruct other images by solving the L1 node back again. So one issue is, up to that point, it wasn't 100% clear to us how would we reconstruct images that are tensor of data, so RGB images, not just grayscale images. So YN is tensor of data. Could be an RGB image or full video full colored video as a whole. Well, to do this, we'll take a detour a little bit and review a little bit of some new decomposition called TSVD. We'll extend this TSVD to some higher dimensions and then reformulate the CSC problem with this new approach. So what is tensor SVD? Well, this paper came in 2011. They proposed a new tensor decompositions that works on third order tensors. And an order of the tensor order is defined as the number of indices you need to slice that tensor. So third order tensor A, another third order tensor B, will apply some tensor operator between them, and the resultant, this is defined as unfolding A somehow in a very structured matrix circ A, and vectorizing B in some particular manner, do this multiplication and fold this back again into another tensor. Now, the structure that goes into circ of A basically is what you do is you take this third order tensor, you put your frontal slices into one big matrix, and then you circularly shift these pieces together. So you get this blockwise circulant level matrix. Well, the nice thing about this is that it turns out that this can be, people show that this can be efficiently diagonalized with tensor product between normalized discrete Fourier transform, which is F, and the identity matrix. And the block diagonals of that thing is basically taking the Fourier transform along the third dimension and then just stacking in these frontal slices into a big block matrix. So the first question is, how would we extend this to arbitrary order tensors, and what is the underlying unfolding of that structure that will happen? So, well, someone would say, okay, just put down HO, call this a high order tensor, and you're done, right? But, well, this is not the point, because we really want to know how is that unfolding would look like once we go from arbitrary ND tensor, and what is the corresponding diagonalization for that property. And in order to do this, I'll give you a small example, and that example is for fourth order tensor. So a tensor of 4 dimensions, n1, n2, n3, and 4. So the unfolding will go as follows. We'll do something similar to the TSVD work. You start, say, with n3, and you vectorize this across n3. So you have n3 blocks underneath each other. So this is still a tensor because we still have the n3 dimension. And we'll apply that trick again where we circular shift its tensor of data. So we get this, what looks like a matrix, but it's a tensor because we still have this green element there. So then what we do is we apply the same exact operations, but on the last dimension. This is n4 in this case. So this whole block has n4 elements. So you see n4 blocks in here given in green. And then we apply the circular shift back again into these blocks, generating this highly structured matrix. And what is interesting is it turns out that this can also be efficiently blockwise diagonalized, in which the blocks are basically nothing but performing 2D Fourier transforms along the last dimensions, take these frontal slices, and putting them into blocks of matrices. And surprise, surprise, that the what almost eigenvectors of this matrix would look like the tensor product of multiple DFT Fourier transforms corresponding to how many dimensions I have with n1. Okay, so this is good. So how can we use this for convolutional sparse coding? Well, what we do now is simply we'll replace that convolution operator with this new operator that we have done here. It's well defined, and we know how to blockwise diagonalize. Okay. Okay, so this is good. But how does this relate to original CSC problem? And how does it relate back again to traditional dictionary learning approaches? Well, it turns out if you select the dimensions properly in a specific way, this particular unfolding of fourth order tensor reduces to, for example, if n1 is 1, this identity is 1, and turns out that it is diagonalized with these operators. And these are precisely the 2D Fourier transforms of some matrix, and this whole matrix is well known in the literature as BCB, which is block circulant with circulant blocks. And thus, this recovers back again exactly the convolutional sparse coding problem under special choices of dimensions. Well, it also relates back again to dictionary learning approaches, in which if we set those convolutional modes or dimensions to just 1, this unfolding becomes just identity mapping. You no longer have blocks, you just have one single block, and this looks like exactly what we'd have for a standard dictionary learning approach, so just a matrix vector operation. Okay, so this is interesting because now we're relating somehow convolution operators in some higher dimension of tensor operator to through this tensor product that reduces to standard matrix vector multiplication. Okay, so the next question is, how would we solve back again this problem? Well, we'll follow up standard techniques in the literature. We'll do coordinate-like descent, just fix the sparse code, update dictionary, fix the dictionary, update the sparse codes. And just because the diagonalization of that operator is actually tensor products of orthogonal matrices, and the tensor product of orthogonal matrices is itself orthogonal. So this is preserved under 2 norm, and thereafter this is known in signal processing community as Parseval's theorem. So we can go back again and update everything with hats, which means those Fourier transform of these variables. All right, so we can do the same trick for these dictionaries one more time. But usually we have one more extra step where we'd like to make the dictionary filters as small as possible, and this is what we'd like to constrain the energy of it, so we can, notation-wise, it is very well defined in tensor theory perspective. Okay, so what are sort of experiments to do, and whom are we going to compare against? So there is a standard data set that we're going to use. It's following other previous works on this fruit and city data set, and split and training and testing for us. Okay, so there are several experiments, but I'll just skip this for now. And but this is basically, we want to compare tensor CC against single channel reconstruction method. And maybe a better representation for this lots of plots here is just one single plot at the far end. So our method is given by TCSC, which is Tensor CSC, and the standard other approaches to construct RGB images, well, the way we did it for them is essentially the way we know is to reconstruct each channel independently. And this is what you see here as SCSC, which is single channel sparse coding. So you see, now we train both methods. Of course, there is a regularization for the amount of sparsity. We train them both at high sparsity domain. Note something that SCSC, in fact, has more parameters than our method, but our method also performs much better at a wide range of testing accuracy, testing sparsity level in terms of reconstruction. Well, one would say, okay, how general are these dictionaries that we learned? Well, the way we do it is we say, okay, I have learned some dictionaries here through using the tensor method. What I'm going to do is I'll extract these tensor of dictionaries. I'm going to use them to reconstruct each channel separately. And this is what you see in green. So tensor TD is tensor dictionary and sparse coding. So the filters that were learned jointly, I'm going to use them to reconstruct each channel separately. And if we did the same for the sparse method, sparse coding method, where we take those dictionaries and try to reconstruct the tensor of data jointly, it also downperforms. So even by replacing our dictionaries that are more generic to reconstruct separate channels, we're still doing better than the baseline method. Okay, so of course there are other experiments, including ablation studies. What happens if we increase the number of filters? Well, as you would expect, the reconstruction will improve because simply we have obviously more parameters. And what you could also now do is you can reconstruct a colored video or tensor of data, just like what we mentioned before. So this is a video which is almost 100 frames, but we trimmed it here. A colored video extraction. So it's like 5D or 6D because of some subtlety that we may discuss later. And what we say is that I'm going to train on those red frames, and hopefully the dictionaries are generic enough to learn the intermediate frames. And also we do a good job at that as well. All right, so that takes us to the last part of the presentation, which by this point I know that, okay, everyone is excited now. Where's the deep learning that you have been talking about since slide 1? Well, just to remind you again, so what we want to do is take a bottom-up approach. We want to look at this block of layer, and we want to analyze somehow this affine layer that could be convolutional or fully connected in some form of generality that allows us to handle this network. And to do this, we're going to really recap on how people used to do computer vision. Is we say, okay, I have a bag of problems that I'd like to improve: compressed sensing and painting, denoising, whatever it is, right? Then you have one of two approaches up until 2017. And the two approaches is the classical method. Basically, you go to the literature, 30 years of knowledge that we know. You throw all the metrics and measures that you are aware of, and you throw them into your FFX, into the modeling part. And then you throw out all the priors you know about the natural images and how they should look like, and you throw that into GFX. You solve the problem, and you have done a great job at it. But then it turns out that you can do even better than that, but just throwing out this knowledge and just collecting lots of amount of data, and we don't have to build any assumptions, train a neural network on that, and you'll get actually significantly improved performances between the two. But I would like to highlight here, it's actually not just the dichotomy of things. There is a spectrum of methods that you can merge and combine between them. And what I mean by this, well, okay, we know from beforehand that this models X very nicely. We know some knowledge from signal processing. Why do we have to throw that out of the window? Well, then, okay, so let's say that I want to solve this problem, and I choose ADMM, and by now you know it's one favorite solver to me. And basically what we say is, okay, what I'm going to do is I look at the update step of ADMM, and one iteration of that corresponds to one complicated layer with lots of intermediate connections, right? And now if you want to add another iteration on top of that, all you do is basically you copy all the parameters into another block, and you pass in the output of the previous layer to the next one. So you have n blocks, but these all n blocks are exactly the same parameters, so you can think about this as a recurrent solver. So what really happens here is basically it seems that running an algorithm somehow looks like doing a forward pass through some architecture. So then this is where the spectrum of methods comes into play. You say, okay, why do I have to guess what are the optimal parameters of my solvers or the dictionaries that I have to learn through some knowledge of signal processing, what we can do is we can fix the structure of each block, the connections between them, but the parameters of each block is different across blocks. And now we can use this Hercules hammer pack again. So the connections within each blocks are given to us from the modeling part or the algorithmic solver that we're going to use. However, the parameters that we usually assume can be learned through an architecture. So these blocks no longer are the same. So this looks like a deep neural network training, but the structure is inferred through the optimization solver. Okay, so unfortunately, this all looks like one directional. So in the future, what usually happens, or even for the past few years, a PhD student says, okay, I want to solve compressed sensing better than what people did before. I'll use the spectrum method that people have been using. They say, okay, this is my problem. What I'm going to do is I'll come up with a new way to construct a network that has structured layers. So they will solve it using deep learning, but the layers are inspired through some optimization method. But this is all one direction. I would really like to go the other way around. So what we want to say is that I have a network that is pre-trained, so I don't worry about the training part. And what I really want to say is this network trying to approximate optimal solutions in the activation functions with respect to some objective function? So is it possible that the output at a given layer is optimal with respect to some objective function, or like if that objective is constrained, it's solution to some KKT sort of problem? And if we have established such a nice connection, then we can go back and see what can we say something as on the overall network, and maybe we could use this knowledge to improve the performance of such network. Okay, so I'll start with a very simple motivational example. So I'll throw out, or I'll drop the dropout layer completely, and I'm going to restrict myself to fully connected layers. I'm not going to talk about convolutional layers for now. And this is what a feed-forward layer in a convolution network would look like. You take your previous activations, XL minus 1, you pass them through the network, you get XL, and this can be represented here through the simple update. Well, I'll try now to do something similar, but I will guess an optimization function. Okay, so fx plus g of x. G of x could be non-smooth, but that's not important for now. And I will just guess the simple function that came to my mind, which is quadratic. However, the difference here is, as I told you before, the network is pre-trained. So I'm not optimizing for the parameters of the network, but I'm saying, is it possible that the output of this network is optimal with respect to some objective function? So what I want to do is optimize for the output activations at a certain layer. And well, you say, okay, this is my objective. A simple approach is just to put down a proximal gradient method to do it. You get this update, and optimal constant step sizes, maybe that's important at some point, will be given as follows. Well, I'll do something extra to it, which is I'll do this for one iteration. I'll solve this for one iteration with zero initialization of XL. What happens, I'll just set L to be 1 for not for particular reason. And what we see is basically that the update for one iteration looks almost identical to this feed forward through one block of layers. Okay, so in order to establish this much more clearly, one way one could ask, is it possible that there exists a function G that has a corresponding proximal operator, this nonlinearity rho? And so this is somehow opposite to what people are used to some extent. They say, this is the function, this is a corresponding proximal operator, we're doing somehow something different. Is it possible that we can come up with priors on the output activations such that the proximal operators of these priors are exactly the commonly used nonlinearities in the literature? It turns out that you can show several well-known nonlinearities through this. So basically, the most simple one is said, okay, if I put a prior on the activation to be positive, well, you can immediately see that this is nothing but a real nonlinear activation. All right, so even more interestingly, it turns out if you do the squared SVM-like loss, the proximal operator for that gives you a generalized leaky ReLU. And why do I mean generalized? Is because now you can also control the slope of the negative term and how much shift do you have in that leaky ReLU. And also if you do something like log barrier-like methods, you get very, very good approximation to also very well-known and common nonlinearities used in the literature in deep learning. Okay, so this is good. We have some nice connection between the two, but there are two major issues that we did not talk about. Number one, how would we generalize this to convolutional layers? And if we did, can we say something about the objective function that represent that? And what is this optimal step size that we'd like to do in order to perform pattern optimization? And where does dropout play a role in all of this? Okay, so let me tell you why convolutional layers are somewhat more difficult than other convolutional layers. So just to recap really quickly, if I have a set of filters given in green and some activations given in blue, what convolutional layers do is nothing but apply some 2D convolutions between two corresponding maps. You do it for a set of activations, and then you sum across these activations. So this operator is linear and everything nice with it, but there are so many things that we don't know about it. For starter, how would we get the singular value decompositions for such a layer or for such a network? Now, neural networks are somewhat more intricate than that, in a sense that they add actually multiple filters. So each one of these filters will give you one output activation. If you have n of them, you have n output activations. All right. So if we'd like to represent this as a big matrix vector multiplication, we don't know the structure of that matrix to represent this operator. And even if we did, we might not actually be able to fit it into memory, not to mention applying SVD on top of it. All right, so given that, it turns out that there is this nice result, which I will decompose for you. So let's say that I have a previous activation layer at layer L-1 of dimensions N1, W1, WH. WH are the spatial dimensions of my activation map, and N1 is the number of channels that I have. And I have a convolutional layers, W by H, N2 by N1. Right? N1 matches this N1, I have N2 number of filters. Well, it turns out that doing convolutional layers is nothing but performing precisely that operator that we talked about at CSC. They're exactly the same, and thus doing a forward pass with this convolutional layer, followed by some nonlinearity, is somehow equivalent to performing one iteration of some proximal gradient method on some objective function. But what is that objective function? Well, it turns out that this is the right objective function that you're looking for. You have this bias term just like before. I'd like to optimize this with some proximal method under this particular operator. Okay, that's good. So how can we say something about the composition of sublayer without actually constructing this massive matrix? Well, because we know nice properties about this operator, we can very efficiently blockwise diagonalize it, and the optimal step size would be something, if we do something like gradient descent, would be given by a max across a set of small SVDs of very small sizes, but massive number of them, so that can be easily parallelized. Okay, but what is even more interestingly is that this operator can be used for the first time to get the singular value decompositions of convolutional layers as well. So this work was submitted and accepted in ICLR 19, and to our surprise, that there was a paper also accepted in ICLR 2018 with the title precisely singular values of convolutional layers, and it turns out they derive exactly the same result. And their analysis is somewhat more details and long, just because they have started with definitions without making the observation that these convolutional layers and fully connected layers somehow equivalent at larger dimensions. So we can actually use the same exact result to do SVD on convolutional layers. Okay, so let's get back to dropout, right? So we know that what dropout do is they kill random activations, let's say 50% of them. Well, this tends to be nothing but performing proximal gradient stochastic gradient method, but choosing a mini patch size. And that mini patch size, of course, as you would expect, corresponds to the probability of sampling these functions. Right, so this is a sum across some elements of this function activation N1, and this is equivalent to doing Bernoulli dropout. Okay, right, so another type of dropout is also investigated in the literature, which is additive dropout. I don't know why do they call them dropout. You're not dropping anything, but you're corrupting more or less all the pixels before all the activations before passing into the linear layer. And this tends to be a one single iteration step from some variance-reduced type algorithm. Okay, so this is the big picture, right? If you change your stochastic solver, we'll keep it to fully connected for now. If you change the stochastic solver that will solve this problem, it gives you different types of dropouts. And if you choose the prior term on your output activation, this is somehow equivalent to changing your nonlinearities. But we also know how to generalize fully connected convolution. We don't have to have this separation between the two layers. Okay, so then how is this useful, right? I mean, we know that this is our solver to solve that objective, and what neural networks are doing are basically canceling this feed backward connection, And what we want to do is want to re-insist on this connection path gain in deep neural networks, in a sense that if neural networks are performing relatively fine, just because they are crudely approximating the optimal activation with respect to this objective, maybe we have a hope of better approximating that optimal objective can help us in getting a better generalization performance. Okay, so there is several set of experiments. The first set of experiments we start with a small neural network, Linet on some cipher 10, and it turns out if you take these blocks of layers and replace them with a recurrent solver, like think with step sizes predicted by theory and so on, what really happens is it turns out that you can improve the generalization performance by significant margins. Now I just want to highlight here is that you see this standard deviation in generalization. This is in forward pass, just because in forward pass we're running a solver and we're randomly selecting elements, and it's actually stochastic at inference time. All right, so we can then move on to a larger network, in this case is AlexNet. We tested on cipher 10 and cipher 100, and it seems that we can actually improve it by almost 1.5% on testing accuracy. Now this might seem to the non-computer vision audience to be not very significant, but I would like to highlight two things. Number one, getting sometimes improvement by 0.7, 0.8 can get you potentially more than a poster paper in CVPR. But not only this, but also because this is the recognition tasks that we're working on is almost very, very saturated. So getting those small niche improvement is extremely difficult. The other thing is that we did not add any extra parameters to the network. Remember, it's the same exact number of parameters, but we're just adding more extra computations to those solvers. Okay, so we can also do more experiments on VGG16 on 2 more data sets, cipher 10 and cipher 100. And it seems that to our surprise also we can push the state of the art up till almost 1% improvement. And I want to highlight again all the baseline numbers that we have collected for these baseline networks. We cannot find any better numbers in the literature or any better numbers in any available open resource repos available online. Okay, so this is just to say that this not might be of a lack of training. All right, so another thing that would be interesting to try out, since we've seen the relation between dropout layers and this mini patch size of this proximal-like method, then do they really correspond in testing accuracy? Well, what you can do is you can train some network and take one of dropout layer and just increase it massively. And you will see that obviously the testing accuracy will drop just because you're killing so many nodes. But what really happens, interesting to us, that which corresponds to minimizing the mini patch size that we're selecting, is that the accuracy also drops, but drops much more gracefully. And the reason behind this is they have these residual-like connections that are applying over and over again. Okay, so this is the end of my presentation, and I'll just really quickly go through the plan that has happened. So I started my PhD more or less in mid-2016, maybe in June or May. And before that, I was doing my master's here in KAUST as well. So I presented 3 works. It's one of them FFTLasso, CVPR17. We have the Tensor work at ICV17. And then I did an internship with Intel and in 2018, which I'm presenting now. This stochastic solver that will be presented in about a week from now. Of course, this is not the end of the journey. There's lots of work that can be done. And I'll just highlight 3 branches of works that go along the same exact line, which is understanding the same block, but we might just want to drop this dropout layer and add one more function because it seems that we can gain some more structure out of it. So the first line of work is that instead of doing this from an optimization perspective, it would be nice to do it from 3 different other perspectives. Perspective number 1 is probabilistic approach, in which we'd like to go through this block and we say, well, the input to this block is some random variable coming from certain distribution. Can we say something about the output distribution? If not, can we say something about the moments of that distribution? So this work led to a work in CVPR in which we show that these results can be extended to larger networks, and you can use them for very various tasks. But there are also several extensions. This is with Mudar, potentially a PAMI submission, and there's a paper and a review for ICV for training these networks at the moment. Another work is interval bound perspective. So we'll go again to the same block of layers. I'll do something more different somehow, in which we say the input to this layer is bounded in some range. So I'm adding infinity ball sort of perturbations at the input of this block, and I want to ask what is the lower and upper bound of output of this network. So why is this important? Well, I'll tell you one example, is that if we manage to show analytically that the lower bound of the correct class label is higher than the upper bound of all incorrect class label, you'll have provable guarantees that this network is robust against infinity norm attacks around that point, of course. So this is a work with Salman. And the last part, which is a tropical geometric perspective, which is again, going back to the same exact block, I would like to represent this block as a tropical polynomial. So think about tropical polynomial as nothing but a regular polynomial, but it has, the operations are defined differently through something what people usually refer to as max plus algebra. Why is this important? Is because now we can ask lots of questions about the geometry that arises from this affine function, and to our surprise, zonotopes are very well known with nice properties, geometric objects arises, and we are able up until now to show that, well, you can use such a results to compress massive networks at VG16 almost by 50% the capacity without affecting the testing accuracy, almost less than 0.3% drop in accuracy. Okay, so this work was in collaboration with so many people, some in CAUS, some out of CAUS. Of course, there's a massive list of Ivy Leagues. Many of them are here, some of them have left already. And of course, none of this work would not have been possible without the help of Bernard. And by this, I'd like to conclude my presentation. Thank you.
All right, so 45 minutes, maybe to the dot even, I think, or even just a minute before. That's great. All right, so the process is that the general audience would ask questions, and then the committee will ask out the questions by ourselves. So let's start with the general audience questions. Who has questions for Adel? Technical questions, please. There has to be one, so you know the drill. Victor, were you raising your hand? Somebody has to ask a question.
Okay. So you remember this link between convolutional sparse coding and convolutional network? Like I didn't get it exactly. Where is the link between convolutional sparse coding and full convolutional?
So I did not actually say that. So it's understandable that you are confused about the link. That is true. So, I said that what I meant to say that there is several works. Let me just jump into. I'm not sure where is. Yeah, I remember. Okay. Yeah, this one. So there has been work that says that convolutional sparse coding during the forward pass of a neural network. So if you train neural network, if you're doing a forward pass, it's somehow like you're solving sparse coding problems at each iteration or blocks of layers, which is coming from applying this ReLU to the previous activations, which ReLU is an approximation to some hard thresholding operator or a soft thresholding operator and so on, which people motivate this by equivalent by 0-1 norm in some sense. And when you do the backward pass to update these parameters, you are somehow doing a convolutional update, convolutional sparse coding update, which is the convolution step of this CSC. And in that work in particular, what people are interested mostly about is that how much sparsity do we need if we model the convolutional neural networks as, neural networks as CSC problem, how much sparsity do we need in the activations to maintain certain representation? But I did not discuss that at all. Yeah.
Okay. Any other questions? All right. So let's leave the room.